Next time you're at the grocery store, I want you to just close your eyes for a second.
Oh yeah, just listen to the checkout lane.
Right. Beep, beep. We have this, like, completely built-in expectation of absolute instantaneous precision.
We really do.
You know, you grab a box of cereal, you slide it across that glowing glass panel, and you just expect the machine to instantly know what it is. It feels clean, it feels binary.
It works or it doesn't.
Exactly. But what you probably don't realize is that little bick, that moment of frictionless commerce, is the result of an obsessively regulated, highly restricted, almost punishing visual language.
It is the ultimate invisible architecture. It's hiding in plain sight.
It really is.
I mean, we are completely surrounded by these little black lines and, pixelated squares, and we just demand that they function flawlessly every single time.
Right, without a second thought.
But the amount of physical engineering, the strict mathematical color theory, and the rigid printing standards required to actually make that happen, it's just staggering.
It's wild. You aren't just designing for human eye anymore.
No, not at all. You are designing a physical object meant to be read by a laser.
And that tension, right, between aesthetic design and literal machine vision is our entire mission for today's deep dive.
I love this topic. It's so good.
Same. We are cracking open Chapter 12 of the book, Graphic Design Reference plus Specification. Our goal is to completely transform the way you look at a simple cardboard box.
Or a restaurant menu, for that matter.
Oh, absolutely. We're going to explore the unyielding, microscopic rules of UPC barcodes, the fascinating physics of color reflectance.
Which literally dictates what colors a graphic designer is legally allowed to use, by the way.
Yes. And finally, the explosive world-building potential of QR codes.
It's a phenomenal journey to take, really, because you're moving from a profoundly strict analog constraint.
One-dimensional lines that can fail if the ink is just a fraction of a percent too bright.
Exactly. Moving from that to the digital freedom of a two-dimensional matrix that can hold thousands of characters.
And survive being partially destroyed, which is crazy.
It's so resilient.
Before we jump into the deep end of all the physics of light and ink, I want to speak directly to you, our listener. We are going to get into some genuinely mind-blowing design constraints today.
Some really nerdy stuff.
Oh, the best kind of nerdy. If you want to follow along with the physical copy of the book we're referencing today, and trust me, the visual charts in this chapter are a designer's holy grail.
They really are.
You can either scan the QR code currently on your screen, or you can find the book link in the description below. And please hit that subscribe button for more deep dives into the hidden systems that run our world.
It's the perfect topic for us, taking something entirely mundane and revealing the chaos underneath it.
So true. So let's start at the very foundation of modern retail, the UPC.
The Universal Product Code.
The grandfather of the checkout line, right? The book defines a barcode as a series of horizontal or vertical parallel lines representing a code that can be optically read and interpreted by a scanner.
Which speeds up pricing at checkout.
Exactly. Historically, the entire point of this was just to stop cashiers from having to manually punch in the price of every single can of soup.
A huge time saver.
But the rules for getting those lines onto a physical box, I mean, I had no idea how militant they were.
Well, they have to be militant because machines are entirely literal. Let's think about how humans read for a second.
Okay.
If you're reading a book and there's a typo, or say a word is smudged by a drop of water, your brain uses the context of the sentence to figure out what the word was supposed to be.
Right, you just kind of fill in the blanks.
Exactly.
Yeah.
A barcode scanner has absolutely zero contextual awareness. It cannot guess. It reads one thing, and that is contrast. Light and dark. 1 and 0.
Wow.
If the contrast isn't deep enough, or if the edges of the lines are even slightly fuzzy, the machine just sees static.
So the data is instantly corrupted.
Instantly.
That makes sense. The book actually starts with the physical constraints, so the where and the how big. Obviously, it says the barcode must be positioned in a highly visible spot.
Right. You don't want the cashier flipping a frozen pizza over 6 times trying to find the tag.
Yeah, we've all been there. But then we hit the scale requirement. The text says a barcode must be printed at a scale between 85% and 120% of its original nominal size.
It's a very tight window.
Yeah, why is that window so incredibly narrow? Like, why can't a designer just shrink it down to the size of a postage stamp so it doesn't ruin their beautiful packaging?
Well, that comes down to the actual physical anatomy of the laser inside the scanner.
Okay, walk me through that.
A scanner doesn't take a photograph of the barcode, it drags a beam of light across it. And that beam of light has a specific fixed thickness.
Ah.
So if you shrink a barcode down below 85% of its standard size, the black lines and the white spaces between them get too close together. They become narrower than the laser beam itself.
Wait, let me make sure I'm really visualizing this. If the laser beam is thicker than the white space?
Exactly. The laser will hit a black line and a white space at the exact same time.
Oh, I see.
The sensor is expecting a binary return, right? Either a sharp blast of reflected light from the white paper or an absorption of light from the black ink.
Good, if it hits both.
If the beam spans across both simultaneously, it gets a muddy, gray, middle-of-the-road signal. It doesn't know if it's looking at a 1 or a 0, so it fails.
That makes perfect sense. And on the flip side, you can't blow it up to cover the entire side of a massive diaper box, capping at 120%. I assume that's because the scanner's window only expects to sweep across a specific physical distance.
Yes, exactly. The optical window, like the actual glass pane you slide the product across, is designed for a specific field of vision.
Right.
If the code is stretched out over 6 inches, the laser just completes its sweep before it hits the end of the data sequence, gets a partial sentence, and throws an error.
So designers are trapped in this tiny 15 to 20% sizing window.
They are completely trapped.
But the sizing is really just the beginning. The printing method constraints are where things get wild.
Oh, the halftones?
Yes. The text is very clear on this. It says, bars must be printed in a solid color, not screen values of spot colors or screen blends of process colors.
This rule is what separates graphic design as an art form from graphic design as, like, industrial engineering.
Explain that, because I feel like people don't realize how printing actually works.
Sure. So when you look at a beautiful, vibrant photograph on a cereal box, you aren't actually looking at solid colors. You're looking at a halftone screen.
Right.
The commercial printing press lays down millions of microscopic overlapping dots of cyan, magenta, yellow, and black ink.
Which is CMYK.
Yes, CMYK. And your human brain is very easily tricked. You step back, your eye blends those millions of tiny dots together, and you perceive a smooth, solid orange or a rich sky blue.
But the scanner is not a human eye, it's practically a microscope.
Precisely. If a designer tries to make the barcode out of a nice screened brown color to match their, earthy organic packaging.
Right, because black would look too harsh.
Exactly. But the scanner's laser doesn't see a solid brown line. It zooms in and sees a chaotic mountain range of microscopic cyan, magenta, and yellow dots.
With tiny valleys of white paper shining through between them.
Yes. It sees a strobe light of reflections. It sees noise. So the standard dictates that whatever color you use for the bars, it must be laid down by the printing press as a single, unbroken, solid flood of ink.
No dots, no blends.
None. Just pure, solid color.
It has to be a solid wall to stop the laser, and that wall actually needs a moat around it.
The quiet zone.
Yes. The book highlights a mandatory feature called the clear zone. It dictates that barcodes printed against a colored field or a busy background must have a color-free area extending no less than 3/32 of an inch, which is about 2.4 millimeters beyond the printed barcode.
In the printing industry, like you said, you'll hear that referred to as the quiet zone.
Yeah.
I always tell people to think of it as a forced palette cleanser for the machine.
A palette cleanser, I really like that. But why does it need one?
Imagine the laser sweeping across a box of frosted cereal. It's picking up the bright reflections of the sugar, the dark outlines of the cartoon mascot's shoes, the text of the nutritional facts.
Just chaos.
Right. The sensor is just processing endless, meaningless bursts of light and dark. It needs a trigger to say, stop paying attention to the noise, the actual data is about to begin.
And that 2.4 millimeters of pure, unbroken white space is the trigger.
It is a moment of total optical silence. When the laser hits that silence, the computer resets and prepares to read the first black line.
So if a designer gets sloppy and lets the edge of a leaf graphic or like a decorative border creep into that 2.4 millimeter zone,
The scanner might interpret the edge of that leaf as the first line of the barcode. The math won't add up, the checksum will fail, and the cashier is left swiping the box back and forth 5 times before just sighing and typing the numbers in by hand.
and we've all been behind that person in line.
We absolutely have.
It's amazing to think that frustrating delay might just be a graphic designer violating the 3/32 of an inch rule.
It's very possible.
Okay, there is one more mechanical constraint here that absolutely blew my mind. It's called the web press rule.
Oh, this is a great one.
The book states, to guard against ink spread, bars should run vertically across the rollers on a web press.
This is where the digital file meets the brutal physical reality of heavy machinery.
I was trying to visualize a massive web press, right? Like, these machines are the size of a house, feeding continuous rolls of paper through heavy steel rollers at high speeds.
They're incredibly fast.
And I came up with an analogy to understand this rule. Imagine you were trying to draw a perfectly crisp straight line with a wet, juicy marker on a moving treadmill.
Oh, I like where this is going.
If you stand at the back of the treadmill, facing the front, and you draw a line parallel to the movement of the belt, meaning you are pulling the marker straight toward you as the belt moves away from you, the line is going to stay relatively crisp.
Right, it tracks straight.
But if you turn sideways and try to draw a line horizontally across the belt while it's moving, the movement of the rubber is going to catch the wet ink and smear it sideways, giving your line a fuzzy, feathered edge.
That's a brilliant way to conceptualize it.
Yeah.
In commercial printing, as the paper is dragged between the massive steel impression cylinders and the printing plates, there's thousands of pounds of pressure.
Right.
Because of that pressure and the sheer speed of the paper moving through the machine, there is always a microscopic amount of what printers call ink squish.
Ink squish.
Yeah. The wet ink physically stretches or bleeds slightly in the direction the paper is traveling.
Which is devastating for barcode.
Exactly. The entire data set of a barcode is encoded in the exact mathematical width of the lines and the spaces between them.
Ah.
If you print the barcode so the lines are horizontal running across the rollers, like drawing horizontally on the treadmill, that microscopic ink squish will make every single line slightly fatter.
And if the black lines get fatter, the white spaces between them get narrower.
Yes. The ratios are destroyed. The code is dead before it even leaves the factory.
But if you follow the rule,
If you rotate the barcode 90 degrees, so the lines run vertically parallel to the direction the paper is moving through the pressing, the ink still squishes.
but it squishes differently.
Right. It squishes at the top and the bottom of the lines, making the lines infinitesimally taller. And the height of the line doesn't matter to the scanner.
Oh.
The crucial width of the lines and the spaces between them remains completely pristine.
That is just incredible. A designer sitting at a sleek Mac in a studio has to orient their digital file based on the literal rotational physics of a 2-ton steel roller in a factory halfway across the world.
It's a beautiful constraint.
It really is. So we know the lines have to be solid, they have to be the right size, they need a quiet zone, and they have to be oriented correctly. But now we have to talk about what color they can actually be.
And this is where we really separate the novices from the professionals. Welcome to the Science of Machines site.
Yes. The book calls this the Guide to Color-Correct Barcoding. And it outlines a fundamental truth, which is that you cannot just pick a color because it fits your brand's aesthetic.
No, you are not designing for human eyes.
You are designing for a red light. The entire system is based on reflectance values.
Yeah, we have to talk about the physics of light absorption for a moment. To a human, a bright yellow box with dark red text looks highly contrasted.
Right, very easy to read.
But standard grocery checkout scanners use a red laser, typically helium neon laser or a red LED.
And that changes everything.
It changes the literal reality of what the machine can see. The scanner works by shining that red light onto the package and measuring how much light bounces back into its sensor.
Okay.
The background, so the paper, needs to bounce a ton of light back. It needs to be a mirror.
And the barcode lines.
They need to absorb that red light completely, bouncing almost nothing back. It needs to be a black hole.
So the book breaks this down into an equation. The reflectance of the substrate, which is the paper, versus the reflectance of the ink. Let's look at the substrate first. The lighter the color, the higher its reflectance value.
Makes sense.
Right. The text gives us some hard data on common packaging materials. Natural craft paper, think of your trendy, artisanal, rough brown cardboard boxes, has a reflectance value of 26 to 43%.
Okay.
Modeled paper is 56 to 77%. And bleached paper, like a stark, bright white box, has a reflectance of 77 to 87%.
Notice how poorly that brown craft paper performs.
Yeah, only 26 to 43%.
Right. It might absorb almost 75% of the scanner's light, only reflecting 26% back. To a human, it's a light brown box. To a red laser, it is a very dark, murky gray background.
So the background is already dark. This means the ink has to be impossibly darker to stand out. The book provides a matching formula table for this. You look up your background reflectance, and it tells you the absolute maximum reflectance your ink is legally allowed to have.
This table is the arbiter of truth for packaging designers. You just cannot argue with the math.
I want to walk through the example they provide because it really highlights how restrictive this is. The text says, if your substrate is natural craft with a reflectance value of 31%, the reflectance value of your ink must be 2.5% or less.
That is extremely low.
Let me push back on this for a second because as someone who loves design, that sounds like a nightmare. 2.5% reflectance is basically Vantablack.
Pretty much. It absorbs almost everything.
So if I'm launching a cool organic coffee brand and my bag is brown craft paper and my brand color is a nice deep forest green, I can't use my brand color for the barcode.
Almost certainly not.
Unless your forest green is so dark that it looks practically black to the naked eye, it's going to reflect more than 2.5% of that red laser light.
Because it's too bright.
Exactly. If the ink reflects 3% and the brown paper reflects 31%, the scanner cannot differentiate between them. The contrast ratio fails. The machine goes blind.
That is wild. The math literally forbids creative expression.
It absolutely does. If you map out the curve of the table the book provides, you see how the restriction scales. If your background paper gets a little brighter, say 35% reflectance, your ink can go up to 3.3%. Still incredibly dark.
Wait, let's jump to the other end of the spectrum. If you are printing on a nice bleached white paper with a background reflectance of 80%, your ink can have a reflectance of 28.1%.
Which is a huge difference.
Yeah, and if your background is a blinding 90% reflectance, your ink can be as light as 38.1%.
Exactly. A nearly 40% reflectance is huge.
That means on a pure white background, you could potentially use a medium blue, a dark orange, or a fairly vibrant green for your barcode, and the machine would still read it perfectly because the white paper behind it is bouncing back 90% of the light.
Oh, for sure.
Oh. Is this why when you buy a bright orange box of cereal or a heavily patterned bag of chips, the barcode is almost always sitting inside a little white rectangular island?
Yes. You decoded the matrix.
I always wondered about that.
Yeah, the designer wanted to use a specific color for the barcode, or maybe they just wanted to use a standard black ink. But the orange background of the box was absorbing too much red light and failing the substrate test.
So they knock out a white square?
They essentially lay down a patch of solid white ink, or they leave the stark white paper unprinted in that spot, creating an artificial high reflectance zone. It's a workaround to satisfy the machine.
I'm never going to look at a bag of Doritos the same way again. That little white rectangle isn't a design choice, it's a mathematical concession to a laser.
And the source notes an important detail about when these tolerances get even tighter.
Oh.
It specifies that these mathematical values are designed for UPC versions A and E in the US and EAN 8 and 13 in Europe. But it specifically calls out that UPC version E and EAN version 13 are small-scale barcodes intended for use on tiny products or containers.
Like a tube of lip balm or a tiny battery?
Exactly. Think about the physical reality of a lip balm tube. The barcode is scaled down to the absolute microscopic limit.
The white spaces between the black lines are the width of a human hair.
When the tolerances are that tight, the reflectance contrast must be absolutely perfect. If the scanner's laser is already struggling to fit between the lines and the ink is slightly too reflective, creating a blurry edge in the machine's vision.
The scan fails.
Right. Tiny codes require the highest contrast possible. Zero margin for error.
So we've established the rules of contrast. We know we need dark ink on light paper. But how does a printer actually make that ink? How do they ensure the chemical mixture of the ink passes the mathematical test of the scanner?
This is where the book dives into what I want to call the 40% danger zone.
Oh, this is probably the most intensely technical part of the entire chapter.
It really is. It maps out the exact reflectance values of 4-color CMYK combinations on uncoded stock.
Right, and for our listeners who might not be familiar with print production, CMYK stands for cyan, magenta, yellow, and key, which is black.
Correct.
By mixing different percentages of these 4 inks, commercial printers can create millions of colors. But the scanner doesn't care about human color theory. The text establishes a golden, unbreakable rule right up front. It says, because colors of the reflectance value of more than 40 have the potential to create scanning problems on a bright white substrate, the following list includes colors with a reflectance value of 40 or less.
40% is the cliff edge. If your ink reflects more than 40% of the scanner's light, it is too bright. The sensor will register it as background noise, not data.
And it gets scarier. The text includes a vital warning note. It says, All reflectance values must be considered accurate plus or minus 5%. Ink quality and printing method will affect reflectance values.
That variance is what keeps print managers awake at night.
I bet.
If you, as a designer, pick a color combination that has a theoretical lab reflectance of 38%, you think you are safe. But the real world is messy. The ink barrel might be slightly less pigmented that day.
Or the factory floor might be more humid, changing how the uncoated paper absorbs the liquid.
Right, or the pressure might vary.
To suddenly your 38% ink dries at 43% on the actual cardboard.
And you just printed 3 million units of packaging that are completely invisible to a grocery store scanner. It is a catastrophic, multi-million-dollar mistake.
So you have to stay far, far away from that 40% edge. Now, the book provides pages and pages of raw data, listing the exact percentages of every safe color mix. We aren't going to read a spreadsheet to you, but analyzing this data reveals a profound physical narrative about how lasers see color. Let's start with the hero of the story, the safe zones.
The scanner loves deep pools of cool tones.
Yes. The data shows that 100% cyan mixed with 70% magenta, which the industry calls reflex blue, has a remarkably low reflectance of just 3%.
Wow.
It is an absolute black hole to a red laser. Even pure 100% cyan on its own only reflects 4%.
And let's connect that back to the physics we talked about earlier. Why does cyan perform so well?
Because it's glue-green.
Yes, cyan is essentially a blue-green pigment. On the color spectrum, blue and green are the exact opposites of red.
Right.
So when the checkout lane's red laser hits the cyan ink, the ink physically absorbs almost all of the red light energy. Nothing bounces back to the sensor. The machine registers a perfect, crisp 0.
That makes so much sense, and it perfectly explains the villain of the data tables, yellow. Looking at these charts, yellow is the absolute arch nemesis of the barcode.
It really is the troublemaker. Yellow pigment reflects red height almost entirely. To a red laser, a puddle of yellow ink looks exactly the same as a piece of blank white paper. It is invisible.
Let's construct a hypothetical scenario to understand how brutal this is for a designer. Imagine you were designing the packaging for a brand new lemon-flavored sports drink.
Okay.
Let's call it Electric Citrus. The entire brand identity is neon yellow. You want to hide the barcode by printing it in a slightly darker mustard yellow. You look at the book's chart. If you mix 100% yellow with 30% black, your reflectance is exactly 40%.
You are standing right on the edge of the cliff. With that plus or minus 5% real-world variance, half your bottles won't scan.
Exactly. So you have to muddy the color to save the barcode. The data shows that if you add more black, say 100% yellow and 50% black, the reflectance drops to 19%. Very safe.
But you just turned your vibrant sports drink brand into a muddy, swampy olive drab?
The black acts as an anchor, dragging the highly reflective yellow down into a register that the machine can perceive, but it ruins the aesthetic.
So what if we use our hero, cyan, to fix the yellow?
The data is fascinating here. If we mix 100% yellow with 20% cyan, we are at 35% reflectance. Still dangerously close to the 40% cliff. But if we bump it just a tiny bit to 100% yellow and 40% cyan,
Oh, wow.
the reflectance plummets to 15%.
That is the chemical tipping point.
Yeah.
Once you introduce at least 40% cyan into the mixture, it absorbs enough of the red laser to completely neutralize the reflective properties of the yellow. The machine can see it perfectly.
It's like an arms race on a microscopic level. The designer wants yellow, the machine demands cyan, and they have to meet in the middle to create a functional green.
Let's look at another complex scenario. What about warm colors? Reds, burgundies, warm browns. A lot of high-end coffee brands or luxury chocolates use these tones. They rely heavily on magenta.
Magenta's tricky, right? The charts show it's not as bad as yellow, but it still reflects a lot of red light.
It does. Magenta is a purplish red, so naturally it bounces a significant portion of a red laser back to the sensor.
Let's say we are designing a luxury dark chocolate bar. The brand color is a rich, warm crimson. We mix 100% magenta and 10% black. The chart says the reflectance is exactly 40%. Danger zone. The laser is struggling to see the crimson against the paper.
10% black simply doesn't have enough physical density to absorb the light.
So we increase the black. 100% magenta and 40% black drops the reflectance down to 24%. Safe for the machine, but now our vibrant crimson has become a dark, brooding maroon.
And what if they try to mix it with cyan instead of black? to make a deep purple.
The chart shows that 100% magenta and 30% cyan gives you a 28% reflectance. But if you hit it with 100% magenta and 100% cyan, you get a 4% reflectance.
Which is incredibly safe.
Yeah.
But 100% of both means you've created an immensely dark, heavy, ink-saturated purple that will essentially look black under grocery store lighting anyway.
Reading the underlying narrative of these charts, I mean, it completely shatters the illusion of artistic freedom in commercial design.
It really does.
A graphic designer probably sat at their desk staring at a beautiful Pantone swatch of a warm, earthy terracotta, and then had to open up these exact charts and realize, I can't use this, the scanner will be blind to it.
Yeah.
I have to inject 30% cyan to cool it down or drown it in black just so a teenager at a checkout lane can ring it up.
That is the rigorous, invisible discipline of the field. You are engineering a tool, not just painting a canvas. And the book emphasizes how high the stakes are. It specifically advises, if it's important to use a color not on this list, check with your printer to see if there's a possibility of using it for your barcode printing needs.
That's serious.
And actually cites its source for all this data, a manual called the Barcode Color Book, published by Symbology, Incorporated, and provides their contact information for further guidance.
Wow.
This isn't just theory, it is a highly specialized, mission-critical field of industrial knowledge. If you guess wrong, the supply chain breaks.
Okay, let's take a breath and step back. We've just spent a massive amount of time in the weeds of analog barcode printing.
A lot of weeds.
We've talked about the precise physical scale of the laser, the chemical reflectance of the CMYK ink, the strict directional rules of the massive steel rollers on a printing press.
Yes.
And all of this intense engineering, all of this mathematical compromise and aesthetic sacrifice is required to transmit, at most, 20 digits of information.
That is the ultimate limitation of the UPC. It was an absolute miracle of its time.
Oh, for sure.
When it was introduced in the 1970s, it revolutionized global supply chains. It eliminated human error at the register. But its capacity is incredibly frustratingly shallow. It only holds numeric digits and a maximum of 20 of them.
It's essentially just a license plate for a product. It doesn't tell you what the product is, it doesn't contain a price, it doesn't have ingredients.
No, nothing like that.
It just gives the scanner a string of numbers to look up in the grocery store's central back office database.
Exactly. The product itself is dumb. The intelligence lives in the store's computer.
But what happens when the physical world needs to hold more than a license plate? What happens when a physical object needs to hold the entire internet?
This brings us to a massive evolutionary leap.
We move from the rigid one-dimensional lines of the UPC to the dense two-dimensional matrix, the QR code standard.
Quick response code. It fundamentally changes the relationship between humans, machines, and physical objects.
The book defines it clearly. It says it's a matrix barcode consisting of black modules arranged in a square pattern, and the capacity upgrade is just staggering. We go from the UPC's 20 numeric digits to the QR code's ability to hold up to 7,089 characters.
Which is massive. And crucially, it's not restricted to numbers.
Right.
The text specifies it can encode virtually any kind of data. Alphanumeric, numeric, and byte or binary data.
I was trying to contextualize that leap, and going from a standard UPC to a QR code is like upgrading from an old 1990s pager that can only display a phone number to a modern smartphone that can transmit an entire novel.
It's the perfect analogy.
And because of the way the QR code is structured, suddenly the graphic designer is allowed to play again. The brutal, punishing constraints we just spent half an hour discussing start to loosen up.
This is a vital point. The source states, standard QR codes can be customized with color, images, and shapes to enhance brand recognition.
Yes.
Because the QR code is a matrix rather than sequential lines, it reads differently. It doesn't rely on a single horizontal sweep of a laser. It relies on a dense, overlapping web of data points read by a camera.
And it has built-in error correction, right?
Yes, exactly. Think of it like a holographic image or even a Sudoku puzzle. The data is redundant. It's woven throughout the entire square. Because of that mathematical redundancy, you can literally delete, damage, or cover up significant portions of the code, and the algorithm can reverse engineer the missing pieces based on the surrounding patterns.
Which means a designer can finally prioritize the brand. You can drop a bright corporate logo right into the dead center of the QR code, physically obliterating 20% of the black squares, and a smartphone camera will still decode it perfectly.
It's a completely different philosophy of machine vision.
It really is.
The UPC requires absolute perfection and unbroken lines because it is fragile. The QR code is redundant, which makes it incredibly resilient. It allows art and engineering to finally coexist on the packaging.
So, with 7,089 characters of flexible data at your disposal, the physical product is no longer a dead end. It is a portal. What exactly are brands hiding in these matrices? How are they activating the real world?
Well, the text gives us a fantastic list of embedded information types, showing how brands bridge the physical and digital gap. The baseline usages are URLs, email addresses, and links to promotional videos.
Right, the basics. Scan this to see our commercial. But then it gets into social media integration, like Facebook or Twitter. You scan your paper cup of coffee on your morning commute, and instantly, without typing a single letter, you are following the roaster's social media feed.
But where it gets profoundly powerful is the delivery of deep, localized expertise. The book uses a great example. It says, for example, a QR code on a wine can provide complex information about the grapes, vineyard, history of the wine, and a wine rating.
Let's think about that from a user experience perspective, because it solves a massive problem in graphic design, which is the physical limitation of space. Say you are at a nice restaurant, or you're holding a bottle of wine in a boutique shop. The label is beautifully minimalist. Just an elegant, embossed logo and the name of the vintage on rich, textured paper. The designer didn't want to ruin that aesthetic by cramming 5 paragraphs of microscopic text about soil composition onto the back label.
They don't have to anymore. The matrix holds the invisible text.
Exactly. The QR code acts as a trapdoor. You point your phone at a 1-inch square on a piece of paper, you fall through, and suddenly you are watching a high-definition video of the winemaker walking through a vineyard in Italy, looking at interactive maps of the region and reading professional tasting notes. The physical label remains pristine, but the amount of information available is infinite.
The text lists other specialized, highly functional use cases too. It mentions event details, noting that a single code can combine the event name, time, a long description, and crucially, geolocation data.
Imagine scanning a concert poster stapled to a telephone pole. Instead of trying to memorize the date or type the venue into your phone while walking, one scan automatically generates a calendar invite, sets a reminder, and drops a pin in your map application with turn-by-turn walking directions. It removes all the friction of data entry.
It also mentions vCards, which instantly save a person's entire contact profile, phone, email, website, headshot into your phone from a single scan of the business card. It lists installation instructions.
Oh, that's a game changer. Imagine buying a complex piece of IKEA furniture. Instead of trying to decipher a confusing 50-page paper manual with vague illustrations, you scan the box, and a step-by-step augmented reality video shows you exactly which screw goes where.
The book also highlights using codes to provide sources for replacement parts and services, direct coupons and special offers, recommendations for complementary products, and customer feedback forms.
The QR code transforms the packaging from a static disposable container into a dynamic, interactive service touchpoint. And the book outlines where we are seeing this physical placement happen in the wild.
Yes. The list includes business cards, brochures and other marketing materials, product tags and packaging, convention and event name tags, restaurant menus, event ticket stubs, point-of-sale receipts.
That last one, the point-of-sale receipt, is incredibly clever. A paper receipt is usually the absolute end of the transaction. You crumple it up and throw it away.
Usually, yeah.
But if a store prints a QR code at the bottom offering a 20% coupon for your next visit if you fill out a feedback form, the receipt suddenly becomes the beginning of the next transaction. It creates a closed loop of consumer engagement.
It's brilliant marketing. But none of this works if the barrier to entry is too high. A code is completely useless if it can't be easily created by the brand or instantly decoded by the consumer.
It's very true.
This brings us to the software ecosystem. Because unlike the UPC, which requires specialized, incredibly expensive corporate hardware.
Right, those massive laser-emitting scales at the grocery checkout lane that are hardwired into a store's central mainframe.
Exactly. Unlike that closed system, the QR code relies on a completely decentralized, consumer-facing software ecosystem. It democratizes the barcode. Anyone with an internet connection can make one, and anyone with a camera can read one.
The book breaks this ecosystem down into 2 halves, generators and readers. Let's look at the creation side first. QR code generators. The text notes? QR codes are created through QR generators. There are numerous free options. Premium generators offer tracking and analytics. A search for QR code generator on the internet will yield many options.
That distinction between free and premium generators is where the entire business model of this technology lies.
How so?
Well, a free generator is static. It takes a piece of data, like a website address, and permanently scrambles it into a pattern of black squares. If you print that code on 10,000 brochures, and then you change your website address a month later, all 10,000 brochures are dead. The code points to a broken link.
Yikes. But a premium generator does something much smarter. The book specifically names a few tools from the era it was written. It mentions Kaiwa, noting it can generate QR code with tracking, analytics, and support. And it mentions UQR, which offers generating capabilities, including customizing the color and format of your codes.
If a brand uses a premium service like Kaiwa to get analytics, they are utilizing a dynamic QR code. This is a crucial distinction. The pattern of black squares doesn't actually contain the brand's website address.
Wait, really? What does it contain?
It contains a unique tracking link that points to a server owned by Kaiwa.
Oh.
When a consumer scans the code, their phone pings the Kaiwa server. In the fraction of a second it takes to load, that server records the exact time of the scan, the GPS location, the type of smartphone the person is using, and maybe even the operating system.
Wow.
It logs all that data into a dashboard for the brand, and then instantly redirects the consumer's phone to the final destination video or website.
Let me make sure I fully grasp the functional reality of that. If I'm a consumer sitting at a bus stop and I scan a movie poster to watch a trailer, I think I'm just passively pulling information down from a poster. But the reality is, by scanning that dynamic code, I am actively pushing a massive amount of behavioral data up to the marketing agency.
It is a two-way street of data harvesting. The generator isn't just drawing cute black squares. It is laying a tracking mechanism into the physical world. If we contrast this with the very beginning of our conversation about UPCs,
Right.
a UPC barcode scans a product to track inventory for the store. A QR code scans a human to track consumer engagement for the brand.
That is a profound paradigm shift. The UPC tells the grocery store manager that one box of electric citrus sports drink physically left the building in Ohio.
Yes.
The QR code on the back of the bottle tells the beverage company that a 25-year-old male using an iPhone scanned the bottle at a specific GPS coordinate in a park at 2 p.m. on a Saturday to unlock a digital coupon.
The value of that demographic and behavioral data is astronomical. It turns every physical product into a node in a global tracking network.
Which makes the user side of the ecosystem, the readers, so important. The brands need us to scan them. The book says once you've created your QR code, users will need a QR code reader, which can be downloaded for any smartphone for free. Now, this section of the book acts as a fascinating historical time capsule.
It really does.
It lists specific third-party applications you had to manually seek out and install.
Yes. The landscape used to be highly fragmented. It lists iPhone QR reader apps like Enigma, Tap Reader, QR Scanner, and QR Reader.
Wow, so many.
And for Android, it lists ScanLife, Enigma again, QR Droid barcode scanner, and MobiScan QR.
I remember that era. You'd see a QR code on a billboard, but by the time you unlock your phone, open the App Store, search for barcode scanner, downloaded it, and opened the app, the bus had already driven away. The friction was terrible.
And that friction almost killed the technology in its infancy. But the fundamental standard described in this text, the mathematical matrix of the code itself, was so robust and so useful that the hardware manufacturers eventually absorbed the software.
Right. Today, the QR reader is just built natively into the camera app of almost every smartphone on the planet. You don't need a clunky third-party app from MobiScan anymore. You just point your camera, and the phone's operating system recognizes the matrix instantly.
The moment the operating system's native integrated the decoder, the QR code truly took over the world. It removed the final barrier to entry, seamlessly bridging the physical and digital divide for billions of people.
Which brings us to the end of our dive into Chapter 12. We have covered an incredible amount of ground today.
We really have.
We've taken a journey from the agonizingly strict analog world of UPC lines, where a fraction of a percent of yellow ink reflectance or the horizontal smear of a printing press roller can completely destroy the data,
to the dense, forgiving, digitally expansive universe of the QR code matrix.
Exactly.
We've traced the evolution from a system designed entirely to appease the limited vision of a red laser, requiring perfect contrast and solid colors, to a system designed for a symbiosis between machines and humans.
Allowing for aesthetic freedom, embedded logos, and thousands of characters of dynamic location-aware data.
It really makes you appreciate the invisible, relentless engineering printed onto every single product you interact with.
It does. Before we go, a quick reminder. If you want to dive even deeper into these visual systems and actually see the exhaustive CMYK reflectance charts that dictate the colors of our world, grab your physical copy of Graphic Design Reference plus Specification by scanning the QR code on your screen or clicking the link below, and hit subscribe so you don't miss our next deep dive.
And I'd like to leave you with a final thought to mull over, building on the trajectory of everything we've discussed today.
Please do.
We started with 20 simple digits in a UPC, strictly designed for a checkout laser. We evolved to over 7,000 characters in a QR code, linking the physical paper to the entire internet via the supercomputer in your pocket. If a simple 1-inch square matrix can comfortably hold that much data, and if our devices are getting faster at instantly translating those matrices into rich, interactive, augmented reality displays, we are rapidly approaching a time where physical packaging might not need written human text at all.
Wow.
If the nutritional ingredients, the legal warnings, the brand story, the assembly instructions, and the promotional videos are all contained within a scannable grid, will the packaging of the future just be a stark, blank white box with a single, highly customized QR code in the center? Next time you pick up a product, look past the colorful graphics and find the barcode. And ask yourself, who is this physical object really designed for? You or the machine?